Thank you for having me. Muthu gave me rather explicit instructions about what my talk should be like. So he told me he wanted me to talk about how I took some theory and I turned it into a company. So for those of you who don't know, if you've been to New York, there's a plant district and a fur district and a this district and that. My daughter claimed recently that we live in the Marc Jacobs district because there are about 8 Marc Jacobs stores within a 3-block radius. Sand Hill Road is where all of the VCs have to be in the Bay Area if they're going to be cool. So this is about taking theory and starting a company. So what's in this talk? I start out by talking about doing some theory, then I got some systems people involved and that made new theory, and then I started a company and that made new theory, and now I have customers and that made new theory. So I hope that's what Muthu asked for this, so this is what you're getting. So what theory am I talking about? External memory data structures. What data structures? Dictionaries like B-trees and cache oblivious B-trees and streaming B-trees. What external memory? The disk access model, the cache oblivious model. Why external memory? Here is where I pontificate for a moment. I grew up doing PRAM algorithms. Muthu and I had the last SPA paper ever on PRAMs.
What year was that?
What year was this? That was like 96 or so. And I consider the death of PRAMs to be like the colossal fail for the theory community. We were all too insecure when these cool people starting thinking machines and all this kind of stuff said, PRAMs are ridiculous. You can't possibly build, that has nothing to do with the machines we're building. It turns out they all went out of business because none of their machines were programmable. Whereas PRAM, you can make all kinds of nice algorithms. We should have stuck to our guns. Anyway, external memory stuff is a natural segue for PRAM people. There are a lot of similar techniques. Why data structures? People say, oh, data structures are useful. This is not why I worked on data structures. They're often maligned by the rest of the theory community as being ugly and detailed and messy and horrible. And I'm a big contrarian, so that holds a big appeal. And Michael Bender, whose name you'll see over and over again in this talk, and I taught a short course, a 1-week course in Buenos Aires in 1999 on the most beautiful results in data structures. And that was the 1-week-long course. Michael didn't know anything about data structures when we started preparing the course, and he thought they were ugly. So this was also my attempt to convince him that he was wrong, and ever since then he's worked on almost nothing but data structures. So the other thing that happened in that course is that I casually mentioned to the organizers that Michael was married to a Costa Rican woman and spoke very good Spanish. And by very good Spanish, I meant he could have a polite conversation kind of thing. He didn't know how to say A plus B. And so they advertised the course as being in Spanish, and we showed up with lecture notes in English. And so I spent the week teaching Michael how to say mathematical things in Spanish. He did a very good job.
How did you know that?
Oh, Spanish is my first language.
Oh.
Yeah. So, and then to paraphrase Feynman, algorithms is like sex. Sure, it may give some practical results, but that's not why we do it. He didn't say that about algorithms, but it's true here too. So, okay, simple problems and simple models. I like simple problems. Here's the dictionary problem. You need to be able to insert X into a set, delete it from the set, look up and get the associated information with a key, successor, predecessor, binary trees, B-trees, etc. solve this problem. And a simple model, the first one is the disk access machine, the DAM. So you can say DAM algorithms and so forth. And you've got memory and you've got disk, and whenever you need something that's not in your memory, it gets fetched from the disk and along with a chunk of B items around it. And then whenever you run out of, whenever you need to evict someone, it gets evicted along with B guys. And, this is typical latency hiding kind of thing. This is slow. So if it's slow but high bandwidth, you fetch a bunch of stuff. And if you're clever, you put a lot of useful stuff near each other. And you get a lot of bang for that buck.
What is the B? I'm sorry.
Oh, the B is the block size.
Oh.
The amount of stuff that gets transferred together. But actually, we're going to talk a lot more about B in just a second. But in the simple model, it's the block size of stuff that gets transferred at the same time. So the goal is to minimize the number of block transfers, and that's basically what we count as the running time. How much we do up here once we're in memory, we don't count that. Of course, you could cheat horribly. Every model has its limits. That's what I'm counting as the number of IOs. They're a lot slower than everything else. And you've got parameter B. M is the memory size, and N is the data size. And B trees, for example, solve this kind of stuff in log base B of N IOs per search or insert. Okay. All right. Cache obliviousness. These people here in '99 came up with this very beautiful thing. Actually, there were all kinds of attempts before cache obliviousness to account for the fact that sequential access is faster than random access on a disk. Muthu and I wrote a different paper in which we came up with some very lame model to try to explain all of this, and then these people did the good job here. And you have the exact same thing going on, but you don't know B. It's not just that you don't know it, you never get to find out what B is. You have to design your algorithm without knowing B, without measuring B. People always say, oh, you start out by sampling to see what B is. No. You can never know B. You can't know anything about it. And you can't know M.
Now, why do you not know B? I mean, don't you know about the technology? I mean, why do you not know B?
I'll talk to you about the talk, but you're asking all kinds of good questions about B, and hold your horses. So they showed that even without knowing B, you could do matrix multiplication and FFT and sorting just as well as if you knew B without knowing B. Okay? And the challenge was, can you do cache oblivious data structures? Because these guys, you get all your data up front, and the computation is regular and recursive, and the main idea is at some point you recurse down small enough that your recursive subproblems fit inside these blocks, whatever the size of the block is. At some point you'll fit, and then you do good stuff, and when you, through the magic of mathematics, it all works out, right? So with data structures, they're dynamic, they're unpredictable, you have to be able to respond no matter what's going on. So here we were in Buenos Aires, eating lots of good food and learning how to say mathematical things in Spanish. And Michael and I started working on this and brought in Eric Domain and showed in 2000 that you can actually match the B tree bound without knowing B. Right? Anybody who remembers what a B tree looks like, you really have like these little blocks that branch according to B. Does anyone know what B stands for in B tree?
Buyer, Rudy Buyer.
No.
He did.
He did, but poor McCrate, maybe they didn't want to call them BM trees, but, but he didn't invent them by himself. Anybody else know the real answer? That wasn't it.
Balance is
It's not balanced. It's not block. It's Boeing. They did the work while at Boeing Labs. All right. So this is sort of a surprising result. It was surprising at the time that you can do this stuff, and also it's sort of interesting because cache obliviousness, you know, the whole fact that it's called cache oblivious. I give Charles Leishman hell about this on a regular basis because he was thinking about it for scientific computing, and so everything was going to be in memory, and you're going to minimize cache line misses and not have to worry about different sizes of cache and la la la. But here I'm doing B trees, and that's all about external memory. And once I had the most horrible conversation with Michael Stonebreaker. I was starting my company, and he had started Vertica a couple of years before, and he started saying to me, what you're doing is nonsense, because cache misses don't matter in a database. I said, I know, it's a bad name. Cache obliviousness is a bad name. Unfortunately, I wrote the second paper, so I didn't get to call it something different. And it has nothing to do with the cache. But he kept saying, but databases have nothing to do with cache misses. So we had this back and forth where I said something, and he kept saying his first position, and I kept saying my first position. So here we are. We're out to external memory. It's not the cache. It's main memory versus external memory that matters. And then there's been a huge literature of cache oblivious data structures. So is it a good thing that there is this big literature of cache oblivious data structures? What's the pros and cons of cache obliviousness? The pros are the results. They're mathematically beautiful, many of them. The model is simple, so you can program it, like that PRAM thing. There's no tuning because you don't need to know B. Right?
I don't know B.
I
keep asking you, you never tell me.
You can run it on different machines. You can run it on the cloud, right? You can run it on a machine without recompiling it, and you can add memory and whatever it is, it'll just chug along. And it simultaneously optimizes for all levels of memory, right? Because it works for every B. It'll minimize your cache misses and your page faults and whatever else, right? The cons are the intros to the theory papers, which stress that there's no tuning and simultaneously optimizes all levels of memory. I wrote some of these intros, and even as I wrote them, I thought, wow, I know I had just been at Google, and I know these really great programmers, and I said, you'd only lose a constant factor, but you don't have to tune. They would be skeptical, to say the least, of the importance. It's like, how bad can tuning possibly be? And as for simultaneously optimizing all levels of memory, which is stressed in paper after paper, it's only the outside one that matters. It's the peripheral one that matters. Nothing else matters. The memory hierarchy is steep. One page miss saved is worth any number of cache line misses. Right? Who cares about simultaneously optimizing? So this was nice, and this was, I won't say embarrassing, because every theory paper has to have a bogus, embarrassing motivation in the introduction, and every systems paper has to have a bogus, embarrassing theorem. All right. So that was the first theory result, and then onto the systems. Pesky asymptotics. We showed that you could do no more than twice the IOs of a B tree without knowing B. Pretty good. It's like the dog that plays chess, but I usually beat him kind of thing. But really, it's pretty bad. Half the speed of a B tree is bad. So, but that's an upper bound. It's 2. What was it really? And so we got Bradley Kuzmal involved. He's this guy who builds systems and talks to theoreticians. So there aren't so many of those. And so we have a patent on him. So we started running these experiments ourselves, comparing ourselves with B-tree. Is it easy to beat a B-tree? And the answer is no. They do a very good job at searches. And they are optimal in the DAM model, if that means anything. To the extent that a computer follows this DAM model, they're optimal. But even on an actual computer, they do a very good job. So we have these 2 configurations. I'm not going to tell you what the small machine and the big machine is like. But whatever, you try all these different block sizes. You might think, oh, well, just pick the page size. Turns out on a real machine, the page size isn't so much what matters, because that's probably 4K. And over here, if you set it to 32K, these are for static. We build the best B tree on a static data set and perform 1,000 random searches. Here we go, 11.9 milliseconds per search. Here it's 14.4 milliseconds per search on this bigger, faster machine. Why is it worse? Well, we had to make it bigger, so the data set bigger so it wouldn't fit in memory. So this is not on the same data set. But this is just for relative comparison. The cache oblivious B tree, which does not need to be tuned, which is why we just have the one number for it, because we don't tune it, took 12.3. So that's much better than 2x. Pretty cool. And on big, it took 13.8, which is better than the tuned B tree. This was an unexpected thing. To actually, without tuning at all or even knowing B, to do better than the tuned thing. And the hardware trends are in favor of the cache oblivious B trees for reasons that are too detailed to get into right now. So how can you beat something that tunes for B? The hint is not because you are minimizing the cache line misses. That was not any part of beating the B trees. And the answer is it's because of prefetching. When here you have RAM and a disk controller and a disk cache, and your operating system is asking for these 4 kilobyte chunks, but the disk controller is going ahead and fetching an entire track and sticking it in the disk cache. And these are of different sizes. And also, if you start asking for lots of stuff in order, it'll go ahead and prefetch several tracks, and it'll do all kinds of prefetching, which means that there's no 1B, depending on how these disk controllers decide on the prefetching, and the operating system's deciding on its prefetching is all rather mysterious. It depends on the load of the disk, the phase of the moon, etc. In any case, it prefetches some prefix of the rest of your memory. It's like today is a prefix of the rest of your life. So new theory came out of that. Cache oblivious algorithms are optimal for prefix prefetching in like an online competitive kind of way. And it's even more than that because they tend to read more sequentially, and the more you read sequentially, the more you prefetch. So in fact, it's the fact that you're using a cache oblivious algorithm gets your disk to prefetch even more.
Is that a theorem or an
That's a
observation?
theorem. It's a very simple theorem. So it's a lemma. All right. So this made us decide to focus on file systems and databases. Like, we're still doing algorithms, but there are all these things in file systems and databases, and we should be able to take our B tree and make an entire cache oblivious file system or something like that. Yes, sir?
So this should still work for SSDs then?
SSDs are an interesting thing that I will talk about at the end. If you look at file system, what was bad about file systems and still sort of is? We went to this HECIWIG, that's High-End Computing Interagency Work Group on File Systems I/O workshop in 2006, and they came up with some grand challenges for file systems. One was to be able to create 30,000 microfiles per second. Lots of systems make these little itty-bitty files and are destroying and creating them pretty quickly, and you'd like to be able to do that. They pick 30,000 a second, using lots of hardware. And the other is just in a system that lets you do this to also be able to traverse the file system recursively, say doing an ls minus a recursive ls at disk bandwidth. Right? A system that could let you update it fast and let you query it fast. And there were things you can do to make this happen or this happen, but not both. And so the question is, what is the root of this problem from a data structural point of view? What about in databases? Well, there's data warehousing where data gets bunched up and pre-sorted before inserting. And so the data is stale but indexed. It's sort of a simple characterization of data warehousing. There are transactional systems where data gets inserted with very few indexes, so the data is fresh but has very poor query performance. And so this is a whole split between OLAP and OLTP, which is a traditional split in databases. And it's the same exact split that we saw in file systems, which is not very surprising, because if you look under the hood in a database and you look under the hood in a file system, you find the same culprit for both, which is B trees. So the entire distinction between OLAP and OLTP is one that depends very narrowly on the performance characteristic of B trees. So let's see. B trees are fast for sequential inserts because sequential inserts in a B tree have near optimal data locality. You fetch in the leaf where you do the inserts, and you insert, 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 and it's in memory the whole time. And then when you finally fill it up, you get to the next leaf. And then, so that's log base B of n, or if you do k in sequential things, it's log base B of n plus k over b. And you get sequential disk I/O. And so people generally pick their primary key in a database to be sequential. If you do ad hoc, high entropy, random insertions, then you have to fetch a leaf here and fetch a leaf there and fetch a leaf there, and you can't have most of the leaves of your B tree in memory, so you're constantly fetching random leaves from disk. And so that's quite terrible, and you get less than 0.05% of your disk bandwidth, typically. So, doctor, it hurt.
0.05% or 0.05?
Percent.
0.05.
Almost nothing. I think almost no bandwidth. You get almost no, like, painfully close to zero bandwidth. Doctor, it hurts when I do this, which is the random insertions. So don't do that, right? How are databases and B trees used? Since sequential insertions are fast, people do sequential insertions. They even have this nice thing. They'll make up a sequential key that has nothing to do with their data. They'll call it an auto-increment primary key, but giving it a name doesn't keep it from being garbage, right? Because it's a key you're not going to use for querying. I'd like to know the average salary of everyone I inserted between 2,357 and it's not, that's just not a good query. Random insertions are slow, so people don't keep indexes that look random unless they're small enough to fit in memory, or they're static and can pre-process them, or. And this is why database administrators have to be trained because of this. Right. Streaming B trees, it's this set of people. A B tree is log n over log b for insertions, and we are log n over b. So plugging in some reasonable numbers, it's like 3 disk seeks for them, and 0.007 disk seeks per insertion for us. That's not percent. Okay, so that's a lot faster. You try that out on some reasonable data, and as long as they're in memory, they're nice, and then they fall off the cliff. And for this data set, we gave up after 14 days. It took us an hour to index that. All right. So they have potential in file systems. At the workshop, those grand challenges, Bradley was there with a laptop, and he measured, and he could beat the grand challenges on his laptop. That was good. But it is very hard to make money off of file systems. File systems, compilers, and land wars in Asia. Right? You don't want. Databases. We solved some important database problems that cut across a lot of databases, but a lot of the legacy workarounds that people use would obscure the performance gains. I'm going to talk very fast now. And also, it's very hard to get something that cuts across a lot of use cases off the ground. But we decided to start a database company because there's no money here, and this may be a lot of work, but there's also a lot of money. All right, and this is some theory that happened because we actually talked to people who, actually built systems. Then we started a company. We made this TokuDB for MySQL as a product we have in the market. It has ACID and compression and transactions and yada, yada, yada. And the first prototype was a couple of months. Now we've been at it for 3.5 years of adding all of this stuff that you need in a database. And why does it take a long time? Well, engineering takes a long time, but also databases are built with the assumption that a search and an insertion take the same amount of time. And for us, an insertion is 200 times faster than a search. So all of the standard techniques that were invented for B-trees over years and years and years for here, we had to reinvent under this different performance model. But we still get this huge performance gain even on a real working system, and this was done by a third-party profiler. And we are horribly CPU bound because when you're doing this many insertions per second, you're exercising the CPU. So we'll be up here when we get done multi-threading the damn thing. Search keys tend to be difficult to search for in general. All right. I'm going to skip this. Customers and unique keys. Legacy is our friend and foe. It's our friend because lots and lots of people use MySQL. It's our foe because people don't want to change the way they use their databases ever, but certainly not until they're convinced that you're the best thing since sliced bread. And the example is unique checks. A primary key generally has to be unique. If you can't have the same primary key twice, and your database will very helpfully tell you if you try to insert a repeated key, it's repeated. On a B tree, you have to fetch the damn page into memory already, so a unique check comes for free. For us, not so much. We can't possibly go and fetch the pages if we're inserting at, with much less than 1 disk seek per insertion. So this is a thing that doesn't make turning uniqueness on doesn't make B trees any worse, but it makes streaming B trees as bad as B trees. If you tell this to a customer, they say, "You do really, really badly with unique checks on," and you say, "We do as badly as you do now." They don't want to hear this message. Bloom filters are a solution for this. They're in-memory approximate membership structures. If the key is present, you report present, and if it's not present, then you say absent usually, but with some low probability, you might say present, one-sided, false positive kind of error. If you set the false positive rates to be the ratio of the insert time to the search time, then you can really reduce the cost of doing unique checks. But if Bloom filters don't fit in memory, they are horrible, and in particular, they're very slow to update, and we have to be updating them as fast as we're updating the B trees. So this is very bad because our sweet spots are large databases, and Bloom filters do not have a sweet spot for very large databases. So we have a new result with this unpleasantly long list of authors called quotient filters, which are in-memory Bloom filters that you can merge, and we use that to make cascading filters where you can go out to SSDs and still get good performance. And check out our upcoming paper on that. But this is theory that we did because customers kept saying, unique checks, unique check, unique checks, and then you can do some fun theory. What have I learned? You have no idea how many times I've heard, "Isn't the theory work done at Tokutech? Aren't you finished with all the theory work?" The initial theory work that I did was a small part of the needed algorithmic work. I used to say that we were a fast indexing database company, and now I say we're the algorithms database company because we keep on doing algorithmic stuff that's under the hood that's needed, and if you weren't an algorithmicist, you'd have an awfully hard time doing it. When it comes to algorithms in a company like this, it's turtles all the way down. So you just, every time you solve one problem, there's another algorithmic problem underneath, and so no, the theory work is not done at Tokutech. The importance of well-designed funding. Let me stress this. We got NSF theory support for the algorithmic work. There's this high-end computing, I don't know what URA stands for. These are some systems people that supported more of the theory work and the systems work, and then a bunch of SBIR money. And it's important to let 1,000 flowers bloom. The original point of this work was that cache obliviousness seemed cool. And it takes a long time to go from cache obliviousness seems cool to a customer reporting that their system goes 80 times faster. That, in fact, took 11 years. And so it is important to have the support of both systems and theory folk at the NSF to do this kind of work and to do this kind of technology transfer. Final thoughts. We're on track for 220 terabyte disks by 2018. People keep on saying that SSDs are going to displace rotating disks, but SSDs are growing less quickly than rotating disks. So they will have their purpose in places where random seeks are the currency of the realm, but if you actually need to store lots of stuff, rotating disks are going to be the place you do it. I should also point out that we kick the ass of B trees on SSDs as well, because B trees are also terrible for bandwidth. They fetch in a page, they make a small change, and then they write out the whole page, and so they kill the performance of SSDs. So filling this disk with a B tree would take 17 years to do all those random seeks, and the disks are only guaranteed for 5 years. Streaming the data on at bandwidth would take 2.5 days, but then you'd get no indexes if you use this kind of system. And even today, you can no longer run RAID 5 on big systems because the time to, if the system is big enough, the time to reformat the disks on disk failure is larger than the expected mean time to failure to the next disk failure. And that's because you're running the file system on B trees. So our SSDs aren't going to save us because B trees also are a poor choice there. And the only way you can use the really big disks is with fractal trees, which is what the marketing people did to cache oblivious look-ahead arrays. They thought that was not a good. They thought that was not a good name, and they thought fractal trees was a better name. And these run at bandwidth. I often get the question, which I'll preempt here, what does Tokutech mean? Toku is a Japanese word, which in French is caché, which means to hide. And caché came into English as cache, and the math was cache oblivious analysis. Fortunately, Toku also can be written this other way, don't ask me why, and that means to profit. Plus, I like French and Japanese food. Thank you.
One quick question. Oh, sorry, Ron handle this
Okay,
first.
so I wrote a paper long ago about the independence of this ratio on page size, which had to do with certain natural systems.
The independence of what, I'm sorry?
Independence of this ratio on page size.
Uh-huh.
But block size didn't really matter in terms of this ratio in certain cases. We could prove it and observe it in certain systems. Does that have anything to do with your stuff about did you observe anything like that, or does that have anything to do with your stuff about not needing to know B?
I'd have to see what kinds of systems. It's certainly the case that as B grows, you only get log of B benefit out of growing B, and so very large page sizes.
Well, if you're not too big, it's good to have a big page size because if you bring extra stuff, it can be bad because you bring in garbage. So
Right, most of it will be
mystery
garbage.
was it seemed to be almost independent of the page. So
That's right.
Yeah.
Yeah. I think it depends on whether you're doing point searches or range searches and la la la. Yes.
You talked about both SBIR and Sandhill Road. Are they compatible?
They are very compatible. There is nothing that VCs like better than a large amount of non-dilutive cash. There's nothing that founders like better either. So yes, that was a selling point. Our ability to raise federal dollars was a selling point when it came time to raise money.